Good morning, everyone. We'll start today with logistic regressions. Before the mid-semester exam, we had finished different variants of linear regression, including regularized linear regression, including basis functions, right? So we had looked at quite a lot of variants. And logistic regression the name is a bit of a misnomer, so it's not really a regression problem, it's a classification problem that we'll be looking at. But it's called logistic regression because of the similarities with linear regression. Last desk, can you please turn off the laptops? The problem setup is a typical classification problem setup. You want to classify, in this case, in a binary classification format between two classes, either oranges or tomatoes. So what we're saying is that let's assume that it's a very simple problem just based on the radius of the particular fruit slash vegetable. You want to tell which particular fruit it is. And we have a few data points. Now, we will be encoding these. Instead of using color to encode, we'll be using the Y value to encode these two different classes. So we're dealing with a binary classification problem. So all four of them, can you please note, they are late, so they won't get the attendance. So please, all four of you, you're coming late, you should not fill up the attendance, or the TA will take the note. So given this problem setup, we've said that it's a binary classification problem, so it's either zeros or ones. Our problem here is that, can we predict the probability of the particular fruit slash vegetable being a tomato given the radius? Why are we talking about the probability here? Till now we have not talked about the probabilities.
So is this probably in terms of confidence of the classifier?
So there are a lot of terms, confidence, probability, sometimes many of them get confused. We will not talk about confidence yet, we will not necessarily talk about what probability exactly means. For now, for us, probability is just a number between 0 and 1. Right? We will not go into the finer details. Where in fact, at some point, we will see that this is not really probability that we calculate. Right? All we are telling is that we want some number between 0 and 1, where we indicate 0 to be exactly, in this case, a tomato, and 1 to be exactly an orange, or vice versa. Sorry? Just 1 second. Yes. 6. Yes, you're saying something. We are, right, but we generally don't need that notion and will not bother about the specifics of it. But just to simplify the setup, we will say that we want to look at probability of y being 1. So, y is our output label. It will be either 0 or 1 for binary classification given us specific input. Right? And we typically do some kind of thresholding. If probability of y equal to 1 given x is greater than 0.5, we say that it's most probably class 1. Otherwise, we say it's class 0. Right? So, there has to be some notion of thresholding that we do. Sorry. So, the key simple idea that we want to use at this stage, we already know linear regression. Can we use linear regression to classify? Right? And this is also similar to one of the questions that I have given in the assignment. Can you use something like linear regression? So in the activity recognition problem, you had 6 classes. right, or 5 classes, whatever, something like that. So I just told, can you predict a number between 0, any number? If it's greater than 6, you call it to be the last class. If it's between, let's say, 1 and let's say if it's 1.2, you say it's closest to the first class, something like that. Can we do that? And so what we're saying is that probability of y being orange given the specific radius, we'll say that let it be a line, theta naught plus theta 1 into radius. That's what linear regression is. Or what we're saying is that let's use probability of y equal to 1 given x is x theta, or if it's a vector then it's x theta, or otherwise x transpose theta. Right? So this is something which we have looked at in linear regression. But what is the challenge here? Why can't we use this directly?
Because probabilities should have values in 0.
Probabilities are restricted between 0 and 1, right? And the x theta would be generally in the range minus infinity to infinity, right? So that's one, and this is what I was saying the prediction could be. Let's say we say that theta 1 plus theta naught plus theta 1 into radius greater than 0.5, then you say it's orange, otherwise it's a tomato, because you're saying that that's a probability dealing with. But given x theta is in range minus infinity to infinity, we can't really encode that as a probability. So that's the first problem. Second, let's look at this initial data set. In this data set, it still seems fine to use linear regression as the way we're using. Let's forget about the fact that it's beyond 0 or 1. Let's assume that you're clamping it to 0 and 1. So you saw that if we just restricted it to the probability of 0.5 and looked at the specific radius, below that radius, above that radius, you can make the distinction. But now let's add one more point. We added one more point corresponding to orange. Now, in order to accommodate that point, you can notice that the line has changed, right? And because the line has changed, and then you put the threshold at y equal to 0.5, probability of y equal to 1 is greater than 0.5, you put a threshold. Correspondingly, if you look at the x, you will notice that one of the orange is now being misclassified, right, as a consequence of 1 point being added. But ideally, what we would have wanted would be something like this, right, a decision boundary like this, which is a straight line in the middle of the, let's say, between these two extreme points. That might have been an ideal scenario. Now, is this setup okay if we add 1 point to the extreme right, one orange to the extreme right? Will it still work?
Yes.
Yes, because you have now split it based on the closest 2 points, right? So it will still work. So there were two problems that we'd seen, and one of the problems, the first problem of x theta being from minus infinity to infinity, whereas you want to encode a probability through x theta. We had already solved this in the second quiz. How did we do that? Using the sigmoid function, right? So sigmoid function brings the values to a range of 0 to 1. So that is the transform which we want to put. So what we're saying is that we ideally want something like this decision boundary. Anything below 0.45 radius is a tomato. Anything above that is an orange. But we typically don't use such kind of boundaries because they're very sharp, they're discontinuous. And we don't like sharp, discontinuous things in machine learning. So what we want is perhaps a simplified, continuous version of this decision boundary, as well as to ensure that the probabilities are between 0 and 1. Right? So if you notice that anything, even if you increase the radius, you will always predict just the probability of orange to be 1, probability of tomato to be 0. And if you go to the other extreme, if radius is, let's say, minus infinity, in this case it's infeasible, but even there you notice that you will always have probability of tomato to be 1 and orange to be 0, right? So you're always between the 0 to 1 range. And if you go between these two slides, can you notice that now if we had applied something known as a sigmoid, we'll see the details, we have ensured that even if you take the x value, in this case to infinity, or x value to be minus infinity, your probability of y equal to 1 after we have applied the sigmoid function will always be between 0 and 1. Right? So, we have got a very nice property which we ideally wanted. So, the idea is we first get y hat as x theta, or x transpose theta. Then we apply a functional transformation, which is sigmoid transform, after which it comes in the 0 to 1 range. So, we use the sigmoid function for it. The sigmoid function has this form sigma of z or phi of z is 1 over 1 plus e to the power minus z. Right. So, can you just think for a minute and tell me what happens when z tends to infinity? When z tends to infinity, e to the power minus z tends to e to the power minus infinity, which is 1 over e to the power infinity, which is 0. So, then sigma of z becomes 1 over 1 plus 0, which is 1. Right. So, when z tends to infinity, we get sigma of z tends to 1. So, therefore, you can notice that sigma of z will always be less than equal to 1. Only when z tends to infinity, it will be 1. What happens when z tends to minus infinity? The denominator becomes 1 over 1 plus e to the power minus times minus infinity, or 1 over 1 plus e to the power infinity, or 1 over 1 over infinity, which is 0. So, therefore, when z tends to minus infinity, you get a 0. So, therefore, you are sure that you will be in the 0 to 1 range, which means it is a good function to be using for the probability, for modeling probabilities.
In one of the assignment questions, we were using min-max scalar. So where scaled values were x minus x minimum upon x max minus x minimum.
Yeah.
Why can't we use
Okay.
it will also give probability the values from 0 to 1 only.
Okay. So, Priyanshi's question is that here we are using 1 over 1 plus e to the power minus z. Why don't we use a min-max scalar, which would also bring the values, let's say, between 0 and 1? Any thoughts on that? So, firstly, you will also notice that when you have to do min-max scaling, you have to look at the entire vector. Right? Here you are dealing with a single value and you can pretty much do it. This is a very simple continuous function which has very nice derivatives and properties, which makes it very amenable. I will also show that this is not the only function you can use. You can use any other function which would have brought it in the range of 0 to 1, right, or some other range. You could have also used a different encoding. Like in this case, we are using zeros and ones to encode. If, let's say, if I gave you a different problem, encode as minus 1 and 1, what transformation could you have then used? Tan h, right? So, there are various such transforms you can use which bring it to a different range, or you start with sigmoid, and as you had one of the questions in the quiz, you can then, so if you get something from 0 to 1, you can always bring it to some other range. You could have also brought 0 to 1 to minus 1 to 1 range. You could do that, minus 2 to 2 range, whatever you want. So, we have looked at the different properties. Okay. And when is sigmoid of z equal to 0.5? When z equal to 0, you can notice from the graph also, when z equal to 0, we get sigmoid of z equal to 1 plus e to the power minus 0, which is 1 over 1 plus 1, which is half. Right? Now, this is a critical point because beyond this, we say that so when we use it to encode the probability, beyond this, when the probability of y being 1 is greater than 0.5, we assign it to class 1, otherwise we assign it to class 0. That's a general convention. No one is stopping you from using a different threshold. Right? You could have used a threshold of 0.6, 0.7, 0.8, and that's where something known as the precision recall curves also come into play. ROC curves, precision recall curves come into play. And as I was mentioning, you could have used other transforms also. This is one well-known transform which works. Okay, now a question for all of you. We have probability of y equal to 1 given x as sigmoid of x theta, or for a single point, sigmoid of x transpose theta, which becomes 1 over 1 plus e to the power minus x theta. Right? Now, can you write this in a more convenient form? Can you write p of y equal to 1 given x and p of y equal to 0 given x and just simplify the expression? So I want you to write something like x theta equal to something, some function of p of y equal to 1 and p of y equal to 0. Can you work it out in your notebooks? In the mid-semester feedback, some of you had asked that we're not doing separate tutorial sessions. One of the rationale is that like such kind of questions, if we did a separate tutorial, I would have directly told you the answer now, and in the tutorial I would have asked you to solve the same question. But I think that breaks the flow, so that's one of the reason we have not done that. But we also did the extra tutorial on the like mock quiz, so we keep doing that kind of thing. Does anyone have an answer? X theta equal to?
in logarithm form? 8 theta or just any number or
Minus will change.
Minus?
Minus of x change plus x.
No, so I want the answer in x theta equal to p of y equal to 1 given x divided by multiplied by something p of y equal to 0 given x. Okay. Let's take one more minute. The important thing to note here is that probability of y equal to 1 given x and probability of y equal to 0 given x will sum up to 1. So you have to use that identity and then you'll somehow get the answer in a more convenient fashion. Okay. Okay. So first I will write probability of y equal to 0 given x as 1 minus probability of y equal to 1 given x. So I have not done anything fancy. This turns out to be e to the power minus x theta divided by 1 plus e to the power minus x theta. And you know that if we divide these two terms, probability of y equal to 1 given x and probability of y equal to 0 given x, I get e to the power x theta, or x theta is equal to logarithmic of p of y equal to 1 given x divided by 1 minus p of y equal to 1 given x. So we can also use this, and if you've done betting, I have not, but this is typically the convention used in betting, which is known as the odds, right? Wins is to losses. When like in the newspapers also you might have seen team A versus team B, what are the odds of winning? So you write P of win over P of loss in the case of betting like setups. We say that odds equal to P of y equal to 1 divided by P of y equal to 0, or log odds is equal to logarithmic of P of y equal to 1 by probability of y equal to 0, which is x theta for the case of logistic regression. So this particular term, log of odds, is x theta. This is also commonly known as logits. So we use two different terminologies to indicate x theta. One is log odds, the other is logits. In the case of machine learning like setup, we typically use the term logits to indicate x theta. Right. So why do we have so much of obsession with x theta? Like, why did I go about this exercise to write log odds equal to x theta? What do you think?
So the information is always in a vector form and we deal with vectors.
Okay, so this is in a vector form. Okay. Any other answer? Yeah. So our obsession with this x theta is that because that's a linear regression problem. That's a problem we know very well how to solve, right? And if you can always bring a new problem in terms of an older problem, for which you already have a solution, it becomes very convenient. And we'll keep on seeing why x theta keeps occurring in this setup. Okay. So what is the decision boundary for logistic regression? The important thing you want to know for decision boundary is, so when would you say decision boundary means where you are unsure whether it's class 0 or class 1? When does that happen? When probability of y equal to 1 is equal to probability of y equal to 0 is 0.5. So can you use this expression and tell me what is the decision boundary? X theta equal to 0, right? So probability of y equal to 1 is same as probability of y equal to 0, which is 0.5. So this entire term becomes 1. Log of 1 is 0. So 0 equal to x theta or x theta equal to 0. Right? What kind of a boundary is x theta equal to 0? What kind of a surface is this? It's a linear surface. Okay. So you can write this as theta naught plus theta 1 x equal to 0, or theta naught plus theta 1 x plus theta 2 x 2 equal to 0, so on and so forth. So that is also linear surface. Okay, so now we come on to the important problem. Thus far we have talked about what is typically known in the neural network world as the forward pass. Given x, given parameter vector theta, I can compute probability of y equal to 1, right? Going forward. So this means going forward. You start with x, you multiply that with theta, you carry out the sigmoid operation over that, you get probability of y equal to 1. But now our question is, we want to learn the parameter vector theta. In linear regression, we had a very simple way to calculate that. We computed the loss function, which was the squared error, mean squared error, sum of squared errors, and then we found out the optimal theta via multiple methods. One was gradient descent like methods, the other was just using the normal equation. So my question to you is, and I've given you the answer also, can I write j of theta equal to summation yi minus yi hat squared, where yi hat is just sigmoid of x theta, or sigmoid, yi hat is sigmoid of xi transpose theta, right? Can I do this? Why or why not? Firstly, in your ground truth, so you have yi. In the case of regression, yi was the real value. In the case of binary classification, what is the range of values that yi can take? 0 or 1. It will take 1 or 2, it will take only these two values. What is the values which yi hat can take? It's a probability of class 1, so it will be a value between 0 and 1. It's not either 0 or 1, some value between 0 and 1. So in that case, this is still seeming correct. There is no problem as such in this setup. So whenever we talk about a cost function, we want to see that if you are misclassifying, your cost should be high. If you are correctly classifying, the cost should be low. So let's consider an example where yi is 0. Right? If yi is 0, if yi hat is 0, then what is the cost? 0. If yi is 0, yi hat is 1, which means you have misclassified the example. It's a very bad misclassification. You get a high cost. That's the highest cost that you can get. If yi is 0, yi hat is 1. So from that perspective, this cost function is correct. There is no issue in that. If you misclassify, you get a high cost, and depending on how much you misclassify, how far you are from the correct prediction, you get a high error, high cost. So there is no problem as such from using this cost function. It might work okay in practice, but we typically don't use this. Firstly, it's a non-convex cost function. So this is the error surface you might see. It's little hard to see, but you can notice that it has a lot of peaks and a lot of valleys. Right? It doesn't have a single global slash. So the local minima that you get are not the same as the global minima, which means it's a non-convex problem, which means that if you were to run a local optimizer like gradient descent, a greedy optimizer like gradient descent, it's very likely you will fall into one of the local optimas. You will not get the global optima. You're not guaranteed to get that. The other reason is that here I've just shown you the cost function, which was also the way I showed you for linear regression, but there are more principled ways to get the cost function, which is something known as maximum likelihood estimation. I will not, so given that we had changed the course code and we simplified the course a little bit, we will not go into the specific details of how we get this particular cost function for logistic regression, but I'll just show that there is something known as the likelihood term, which is you try to model the probability of data given theta, and then you apply something known as the Bernoulli distribution. And if you just follow the derivation, you get something known as the log likelihood term, and then if you just set j of theta, the cost function, to be something known as the negative log likelihood, that becomes your cost function. We study this in detail in one of the courses which follows this course, probabilistic ML. So we write j of theta to be minus logarithmic, outside logarithmics there, and then the product over the n examples of 1 over 1 plus e to the power minus xi transpose theta raised to power yi. Yi, remember, is the ground truth, so it's either 0 or 1, and then 1 minus 1 over 1 plus e to the power minus xi transpose theta raised to power 1 minus yi. Now, given that log of products can be written as sum of the logs, that way you can simplify this expression to be, and logarithmic in the power, so the power comes here, and you convert the product to sum, so it becomes minus I equal to 1 to n for the n examples, yi log of sigmoid of theta xi. This can also be written as just y hat I. Right? If you remember, y hat of I was probability of y equal to 1 given x and theta, which was same as sigmoid of xi theta. Right? So this is an easier way to remember. Minus I equal to, so minus outside, and then summation I equal to 1 to n, yi log yi hat plus 1 minus yi log 1 minus yi hat. So this particular function is known as cross entropy. Any thoughts why? Why do we call this a cross entropy loss? What was the formula for entropy? Minus summation pi log pi, right? So there p and log p terms that you had were same, right? Logarithmic of the same term as the weighing, as the weight for that function. Here you notice that the weighing is over yi and the logarithmic is taken over yi hat. So you have two vectors, one is the y vector, one is the y hat vector, and you are looking at the cross terms. Minus yi log yi hat plus 1 minus yi log of 1 minus yi hat. Right? This is fairly similar to minus p log p, but the logarithmic term, instead of writing p, you have a p hat term. Right? So minus yi log yi hat plus 1 minus yi log of 1 minus yi hat. You can also notice this as this is yi logarithmic of probability of class 1 plus the probability of class 0 times, not the probability, the ground truth class 0, logarithmic of probability of class 0. Right? So we can write it that way also. So everyone clear on why we call this the cross entropy? Right? So you have to remember the entropy formula, and you have to note that here we have the cross terms between y and yi hat. y hat. So previously I had mentioned when we were discussing the squared laws, right, I had given you certain attributes of what makes a cost function an appropriate cost function. For classification, if your classification is correct, you should have a low cost. If you misclassify, you should have a high cost. Right? That's the fundamental property which we want a cost function to have. We'll look at the same property for this example, for the new cost function, cross entropy cost function. To simplify this, we will write this previous cost function for a single example. Right? And so that at least the summation goes away. It makes our life simpler. If I had a single example, I would write my j of theta to be minus yi logarithmic of yi hat minus 1 minus yi logarithmic of 1 minus yi hat. Right? Now think of the, so maybe you want to draw this out in your notebooks. Consider the case when yi equal to 0. Right? Now with respect to yi hat, can you draw the cost function j of theta? How will it look like? So draw the cost function plot for j theta given yi equal to 0. You can go about finding the answer from two perspectives. One, you can just plot the functions. Second, you already know that this is an appropriate cost function. You should see that when yi and yi hat are varying or they're very different, then the cost is high. And when they're similar, the cost should be low. Okay, does anyone have an answer? So firstly, if yi is equal to 0, and you have two terms in this expression, does the first term become 0? And the second term is just minus 1 times logarithmic of 1 minus yi hat. Yi hat will always vary between 0 and 1, that's all you need to now plot. So minus logarithmic of 1 minus yi hat, where yi hat varies from 0 to 1. You have to make that plot. Sorry? Okay, let's look at the plot. When y equal to 0, yi equal to 0, firstly the first term becomes 0. The second term becomes minus 1 minus yi is 0. So, it becomes minus 1 times logarithmic of 1 minus yi hat. Yi hat varies from 0 to 1. When yi hat is 0, you get minus 1 into logarithmic of 1, which is 0, right? Which makes sense. When y and y hat are the same, there should be no cost incurred. There should be no loss because you have correctly classified the example. When yi hat or y hat tends to 1 and when y is 0. So, it means you have perfectly misclassified the example. You should incur a very, very high loss, which is what you will see. It will tend towards infinity, it will be a very large number. Typically again, because you are trying to represent these things via a computer, it will not be exact infinity, it will be a large number. And you not have, you typically not get y hat equal to 1. Why? Why is it hard to get y hat equal to 1 or very close to 1? So, y hat comes from sigmoid of x theta. A sigmoid of x theta will become very close to 1 when x theta is very close to, when x theta is infinity, which we will typically not encounter in practice. So, therefore, we will typically get y hat to be a large value, but it will not be equal to 1 ever, right. Okay. Can you now take one more minute and make the plot, similar plot for the case when yi is 1. You should again just be able to draw inferences from this, learning from this, and be able to generalize. When yi equal to 1, how does the plot for j of theta look like? Okay. When yi is 1, you firstly notice that the second term becomes 0. So, we do not care about that. We only have to care about the first term, which is minus yi log of yi hat, and yi is 1. So, this is basically j of theta equal to minus log of yi hat. When yi hat is 1 and yi is 1, we incur 0 loss, which is again good for us because both of them are correct, like you have correctly classified this particular example. But when yi is 1 and y hat is close to 0, it is a case of perfect misclassification, and in that case the cost would be tending towards infinity, very large cost. But again, why does this not typically happen in practice? Why do not we in practice encounter yi hat equal to 0? For that, x theta will have to be minus infinity, which is like generally not feasible. If we look at this particular cost function, which is the cross entropy loss, and if we make the contour plot and we make the surface plot, you can notice that this is now a convex function, which is good for us because it means that we can just run a favorite local optimizer and we should be able to reach the global optima. Now, in practice, you may see that whenever logistic regression is implemented, it is typically not implemented using first order methods. Can you give me some example of first order methods? Gradient descent and variance. It is typically implemented using second order methods, which is, let us say, Newton's method or equivalent, which works well in practice there. Now, a few minutes back, I had mentioned about the term logits. Right? Can someone remind me, what do you understand by logits? What was I using the term logits for? What is logits?
Log of probability of
log of probability of y equal to 1 by probability of y equal to 0. That's one way. Otherwise, logits was just x theta or x transpose theta for a single example. Now, we will see why using logits makes a lot of sense in terms of the loss functions. Okay, let's look at this code. These are my y vectors. This is my y vector, ground truth vector. Typically, it's always either a 0 or a 1. For some reason, let's say that I've given you the probabilities, right? It should be either 0 or 1, but for some reason, I have just given you the probabilities. It should not really matter. Then I have the model logits, right? So, model logits means that these are the x theta values which I have obtained from my logistic regression model. Right? I have just done x into theta and I have obtained minus 2 and 2. Once I obtain my logits, which is x theta, I apply the sigmoid function over that to convert into probabilities. So, I can then apply sigmoid function and then I can get my probabilities. Right? Nothing confusing till now, I hope. Now, once I get my probabilities, I can then pass into my binary cross entropy loss function. I give the model probabilities and I give the ground truth probabilities. Again, ground truth probabilities is generally 0 or 1s, but here we are looking at some real values. That's if I am using the probabilities. I can use this cross function, this cost function. There is another loss function used in Torch, which is known as binary cross entropy with logits. So, in this logits, I am directly passing in my logits. You can notice the highlights also, instead of passing in the probabilities. If I have to pass the probabilities, I have to first convert the logits into probabilities via the sigmoid transform. But let's say I don't need that, especially in this loss function. Now, if I run this, you notice that my answer is the same for both, right? So, with this, why should I even bother about logits? What do you think? So, my question to you is, logits and using the cost functions, using the loss functions which are optimized for logits, it's better than using directly, than converting them into probabilities and using. Why? Continuity, no. So, it's a continuous function. It's a monotonically increasing function. So, it doesn't have that issues.
Higher decimal place is different, so maybe when we convert, there is some loss.
Okay, you tell me what you want me to change in line 11. So, the hint is something if I change in line 11, then these two numbers will start differing.
Should we increase the range?
Tell me some values.
Let's say at least 7, because for graph truth we are considering probabilities from 0.
Okay, so if I make this minus 2 7, because these are x theta values, they are minus infinity to infinity. I can put any values.
So it should either be minus 7 or the first value should it be greater than 7?
No, the first value can be anything. This is just x theta.
Okay.
X theta can be any value. Right? So, let's say with 7, he says 7, still nothing changes. What do I need to do in order to show that there is some problem with converting into probabilities?
We are inverse. We are applying function and then also inverse.
I mean, that's one way to look at it. You are doing more operations. Okay, who said 100? Okay, let's put the 7 to 100. Nothing changes. Someone says make it smaller. So, let's say I make it minus 2, minus 50. Okay. I still get the same answer. So, I need you to break something here. Something in the first, someone in the first column. I have not had any answer there. Okay, second last row, first column, anyone? Okay, second from the left. I just want you to give me some numbers. It will either work or not work. What do you want to convert it to? 0? 0 works perfect. Okay. Let me change the 100 to 300. Now the numbers have changed. Right? If we saw 100, this was 35.34. If I change the 100 to 101, 35.34, 35.69. If I change this 101 to 121, 35.34, 42.69. What is happening? If I'm using the loss using probabilities, is it getting stuck at a particular value? Right? What could be the issue?
Because probabilities as you have defined it as limited to 0 and 1.
Yes.
So in the other range as well it is translating to a particular region. If we cross a particular threshold, the probability is still limited, but the logic function is not.
Okay. Good. Let me show you even more. You can again see when I'm using probabilities, it gets stuck at a particular number. Now, can anyone pinpoint and tell me why this is happening? You've given, sorry? Floating point limitations. But why do those occur? Okay. Let's say that we have a sigmoid function. I am using my own sigmoid function, which is 1 over 1 plus e to the power minus z. For minus 90, I get exactly 0 as an answer here. Minus 80, I get a very, very small number. So if I go minus 83, minus 85, minus 87, minus 88, 89. Yeah. At this point, beyond this point, your sigmoid will always give you a 0, exactly 0, right? But you don't necessarily need to convert this to a probability. You could have directly used the loss function, which is dealing with the logarithmic scales, right? So because of this issue, you will have these errors when the values of x theta are very small or very large. They'll be thresholded to zeros and ones. Whereas in the case of when you directly use the logits and the loss function, which works directly with the logits, you will not have these issues. Okay. So this also suggests highly, like this is why I highly recommend that whenever you are trying to implement logistic regression like variants or even neural network like variants, it's very safe to work with logit space and then use loss functions which directly take logits. So when we deal with neural networks and multi-class classification, we will see that in the next lecture also. We have a generalization of the sigmoid called the softmax function. We will have the same issue there. Right? But it's always recommended to use the logit space. Your model outputs the logits and then your loss functions works with the logit space. Now, in the previous year's quizzes, I have always asked a question around this. So if you want, you can just note down this particular topic. We're dealing with underflow, overflow, we're dealing with logits, why should we use logits, we're dealing with why particular cost functions might work better. So something around these. And because we have seen that how this particular loss function is and how we can use logits, I will now show you a very, very simple implementation of logistic regression using Torch. The important thing here is that this building block is the simplest building block which will help you get to neural networks, as well as this is very simply connected to what you do in linear regression. So I define a class called logistic regression, subclassing from nn.module. The important thing is that I have a single layer, we call this a layer, This is basically nn dot linear input dimension comma 1, right. So, let us say my input dimension is 2. This means that it will give me 3 parameters, theta naught, theta 1, theta 2. That is what nn dot linear will do, right. For now, we are just dealing with input dimension and the output dimension is always 1 in this simple case. We will look at multi-class classification in the next class. But nn dot linear input dimension is, if it is 2, it creates my parameter vector theta naught, theta 1, theta 2, which have to be learned via gradient descent like operations. My forward method, which I have been talking about, this forward method, is once you have your input x, once you have the parameter vector theta, you can do x transpose theta or theta naught plus theta 1 x1 plus theta 2 x2 to get your x theta. And what am I saying, that how do I represent x theta as? What do I call x theta in logistic regression? As my logits. So, I say that my logits is self dot linear of x and I just return my logits, right, as simple as that. I use this simple data set which is known as the make moons data set. Is this data set linearly separable? No. So, would you be able to get would you be able to classify this using logistic regression? It's a loaded question. Would you be able to classify this using logistic regression? Why or why not? Why do you say no?
It's not possible to get a linear.
So, my question was, will you be able to classify or not? Of course, you will be able to classify. It may not be an accurate classifier. That's why I said it's a loaded question. And what kind of accuracy do you think you will be able to get? Less than 0.5. Okay. Any other guesses? Who says between 50 and 60? Who says between 60 and 70? Who says between 70 and 80? 80 to 90? Okay, who says 82.2? So that's the answer we'll get. Again, it seems weird, but you'll be able to get 82.2% accuracy with this. You can always draw some line which will be able to get a lot of the points correct. We'll see how in a few minutes. Now, as I mentioned earlier, that whenever we build models, it is always a very good practice to run the model without training first, to see what kind of predictions you get from an untrained model. And that is exactly what I'll want you to do first. I create a logistic regression object. I pass in the variable 2, which is my input dimension, because my input dimension is x1 and x2. Right? And these are the two classes, so it's a binary classification problem. I have done my favorite mesh grid, and then I want to plot on the entire grid. So, this is the forward pass. I get my logits from my model on an x value that I give. I can then convert the logits to probabilities by passing it through the sigmoid function. Okay, what do you understand from this plot? This is my probability of my color bar is showing probability of class 1. What do you infer from this plot? Apart from the fact that it's an untrained model. So, these are classified to be 1 and the threshold is typically 0.5, right. So, something around this is the boundary which an untrained model is giving. Now, if I have to optimize this model, I am just using this typical gradient descent like operations. I am here using Adam. I get the parameters from my model. In this case, my parameters are what? What are my parameters of the model? Theta naught, theta 1, theta 2. You can verify that also. Okay. Do you see 3 parameters? Right? So, typically when you write in the neural network libraries, these parameters known as W vectors and the B vector, Wx plus B, which is theta naught plus theta 1. So, theta naught is typically written as B as the bias term in neural network libraries. You have theta naught equal to some B term equal to minus 0.35, and then you have the theta 1 and theta 2 term. Right? So, you have 3 parameters which we have confirmed because the input dimension was 2. Now, this was also one of the questions which I had asked in the second quiz, that you have to run the model till convergence. And I specifically defined convergence as when the difference between the loss between successive iterations falls below a certain threshold. Right? So, the way I have done this is, firstly I am using a while loop. You could also do this using a for and use a break, etc. I firstly put converged equal to false. I put my previous loss equal to 1 E8, I have just put it to be a very high initial value, and I equal to 0 to initialize the number of iterations. I first get my logits via the model, and I am passing this on my inputs x, nothing new in here. For my loss, I am using my binary cross entropy with logits loss. So, this is where I think Torch gives you multiple options. You could either use the functional API or you could use the object oriented API. In this case, I am using the object oriented API. I pass in my logits and I pass in my tensor y. Now, importantly, as I mentioned earlier, your y would be either zeros or ones, right? So, y is corresponding to the 2 classes, it will be either zeros or ones, perfectly zeros or ones. And this is where I am checking for if my model has converged or not. So, I wanted you to write something similar to this in your quiz. If the previous loss minus the current loss, the absolute value of that is less than the threshold which I had given, then you will say the converged is true, otherwise it will keep on continuing with converged equal to false. Now, of course, Torch-like libraries provide methods to do this more efficiently, but I had just shown a very simple for loop in case and conditions if you wanted to check. If I run this, you will notice that the loss goes down to 0.267. It started with the initial loss of 0.58. And now, if I plot my predictions, now can you see that it's a fairly decent prediction, right? The learned classifier. All of this is probability of class 1 equal to 1, all of this is probability of class 0 equal to 1, and in between in this yellow region, you have the decision boundary, which is probability of class 1 equal to 0.5. Oh, actually the numbers, the numbers I was telling was 82.2 is not for this data set, it's for some other data set. We may end up getting much lower numbers here. So, if you wanted to get those numbers, you may write something like no grad right. So, you get the logits. Now, you are trying to get the numbers on the training data set itself. You have not really done a training and test. You get the logits as running my logistic regression model, which has been now optimized, whose weights have been optimized. I get the probabilities. If the probabilities are greater than 0.5, I just convert it to a 0, 1 vector through this way. Right? And then I look at my y prediction equal to y. Oh, actually I get 86%. So, could I have written this loop, could I have written this function without using probabilities? Think of this as a quiz question because we have already discussed the answer. Do I necessarily need to use the probabilities, probs variable here, or can I skip that and still get the same 0.6 answer? I can use logits. How? What is probs? What is this line telling me? Probs greater than 0.5 telling me. Yeah, probs greater than 0.5 is the same as logits greater than 0. So this is your decision surface, right? So we could have also written this as, forget about the probabilities. Logits greater than 0. I get the exact same answer. Okay? So this is another advantage. You don't need to use sigmoid, right? Although in the whole formulation, we start with sigmoid probability, we start with something between 0 and 1, etc. But for classification, you don't need. Every lesser operation means lesser chances of making mistakes, lesser time to compute. The other thing you might have noticed in my answer, in this particular code, is that I'm using something known as torch.nograd. Does anyone know why I'm using this particular line? Does anyone know what it means when I write with something in Python? What is it called? Context manager, right? So within this specific context, I'm doing something. So in this context, I've set torch.nograd. What do you think this means? Why do you think I'm using that? If I didn't write this, I'll still get the same answer. So this is at the time of prediction, right? At the time of prediction, do I need to create a computational graph? Do I need to compute the gradients? No. I need to compute the gradients only when I'm learning, only when I'm doing the training process. At the time of testing, I don't really need the gradients, which means that I can simplify my computational graph to not include any gradients, which means that I can reduce the amount of memory being used. So this is one mistake I've sometimes seen students do. They, even during testing, they unnecessarily compute the gradients. So we can actually see this. So if we do print logits, you can see that logits is some tensor, right? In this case, logits is some tensor. I will now copy paste this code and remove this context manager. I still get the exact same vector, but I also get this grad function equal to AD backward 0. Right? Do you see that this specific grad function being computed? So this is probably addition, there is some matrix multiplication. is generally matrix multiplication. You'll also see something like generalized matrix multiplication and torch like things, and then there's a backward method. We'll study more of this when we study when we study automatic differentiation. But even till we reach that stage, I think this is practically useful to know that there is no need to compute the gradient functions and the gradient values. So we can skip all of that at the time of prediction. So therefore, it's always recommended to use torch.nograd like functions. Any question in this notebook till now? We've looked at a lot of tricks, which typically we which typically we are a tutorial like subject. We don't really need to cover them in theory. Some of them being used logits wherever possible. Use the loss function which is optimized for logits wherever possible. The other benefit you'll also get is that now the loss function which directly deals with logits, it's also optimized, right? So you don't really need to go through the probability, that sigmoid and the sigmoid inverses kind of thing. Some of these things are already stored as in the computational graph. So that also makes it efficient. Beyond that, we have seen that how to check for convergence. This is one specific variant which I've seen when the loss does not change beyond a particular point. Does anyone know of any variant of this? Any other variant you could have used for convergence? I've taken one variant where the loss is not changing beyond a certain point. What else could I choose? Let's assume we don't have a validation set. We have to do something on the training set only. When the gradient is very small, okay, excellent. What is another way to, so gradient being very small, can you quantify that further? Like I can't, gradient is small is not maths. How do you quantify that? Like just tell me a statement. Like here I had this statement, np dot absolute of previous loss minus loss dot item is less than a certain quantity. The loss is a scalar, right? So in terms of losses, it's very easy to write. Previous loss minus current loss, absolute value of it is below a certain threshold. It means I've converged. L2 norm of the gradient. Now the gradient is a vector. You can take the L2 norm of the gradient. If it is below a certain threshold, it means that the gradient is not being updated. That's one. What could be yet another way of coming at the same quantity? So we've looked at the gradient, we've looked at the loss. What is the only other term which is left? Parameters theta. You can also look at the parameter theta, and if the parameter theta is not changing by a certain quantity, it's changing in theta is less than a certain quantity, which is similar to the gradient, then also you can say that you have converged. Right? So we've looked at now 3 different variants of convergence. Typically in practice, you have much more sophisticated variants of this. There is something known as the patience term. Patience term, PATIENC, which means that if your gradient is not changing beyond a certain threshold for some number of iterations, that is when you stop. Suddenly it also seems that your gradient doesn't change in 1 iteration, 2 iteration, 3 iteration, or sorry, your parameters are roughly constant, but after 4 or 5 iterations they suddenly drop, they suddenly change. So therefore you typically have something known as patience term also. So these things you can find in learning schedulers. Right, so this they mention about reducing the learning rate, etc. So another thing which is typically done in practice is that you don't keep the learning rate to be constant, you reduce it over time. And I think reduce LR on reducing learning rate on plateau. Plateau means that your loss is not changing, you've hit a plateau like stage. So this is where I was mentioning they have something known as a patience. Number of epochs with no improvement, after which learning rate will be reduced. So you keep running, and if the loss has plateaued, it's not reducing, then after some number of patience, number of epochs, you will reduce the learning rate further. Okay, I think this is a good point to stop. In the next class, we will be doing some bit of maths in order to compute the gradient descent update rule, and then we'll go on to multi-class classification using logistic regression. Thank you. Can I have the attendance sheet, please?